As we've talked about change processes, we've talked about different sorts of constraints that one can put on a process that defines the path as we might draw it in a PV diagram. I mentioned adiabatic processes early on, but I haven't really talked much about what that means. So let's spend a little bit of time talking about that so that we can get acquainted with these processes. So an adiabatic process is basically one that's going to imply that it's taking place under conditions that cause the heat exchange between the system and its surroundings to be zero. All right, there's several different ways that one could manage this, and I won't go into those details, but I do want to say that this is not the same as isothermal, which is basically we're not going to change the temperature. All right. You could still have a temperature change without exchanging heat with the environment if you have internal work that converts the temperature that you have in your system. All right, but in this case, we're going to say there's no heat exchange going on with the environment, so it's presumably a process that is taking place with insulation between the system and the environment. I'll also mention that adiabatic changes are typically associated with slow, reversible processes. So I want to make that notation so that we're clear about that. Now, what I want to do is I want to examine the thermodynamics of this in such a way that we can begin to construct what an adiabatic path might look like on a PV diagram. All right, so this is going to involve a little bit of math, and so I'm going to apologize in advance that I'm going to go through some math here. Some of this math is shown in part of the text that you'll have as part of the lesson, but I'm going to show you how some of the final results are gotten, which means I'm going to go into a little bit more detail. If the details are not to your liking, that's fine. What I'm going to ask you to do is pay attention to the end result, okay? But hopefully by seeing how that end result came about, it'll give you a little bit deeper appreciation for this. All right, so in general for a process, we're going to relate the change or the incremental change in heat can be related to the internal energy plus PdV. We've seen this expression before. But what we haven't done before is I want to rewrite this internal change in heat to be CV dt. All right, so this is going to be relevant for probably a gas, an ideal gas. And the PdV will keep the same. So we're going to basically write our change in heat, our incremental change in heat, is equal to the heat capacity at constant volume times dt plus the pressure times dV. Now, since this is equal to 0 in an adiabatic process, that means this whole thing is going to be equal to 0. So what does that mean for us? Well, I want to take these two terms and the fact that they add up to equal 0 over here to explore a little bit about how that will define a path for us in a PV diagram. Okay, so what we're going to need to use is the ideal gas equation of state, and I'll write that out here. So that's PV equals RT for 1 mole. I'll still continue to use 1 mole. And so we'll also have that the pressure as a function of volume can be written as RT over V. So now I'll put that into this equation, and what we'll end up having is something that looks like this. I'll have CV times the differential in temperature plus RT over V times the differential in volume, and that's equal to 0. Now, one way we can manipulate this a little bit is to take this whole equation and divide through by the temperature. And I suppose as long as temperature is not at absolute 0, this will be okay because we can divide by any number. When I do that, I'm going to end up with an equation that looks something like this. I'll have CV over T dt plus R over V dV is equal to 0. And now what I want to do is move this part over to the right-hand side. So I'll have R over V dV is equal to minus CV over T dt. Now, why have I done all of this? Well, this is meant to be suggestive because everything over here depends only on volume. And everything over here depends only on temperature. So I have one thing over here, a differential expression that depends only on volume, and one thing over here, a differential expression that depends only on temperature. So I can actually integrate this equation. Whenever you can separate these variables like this, that means that this represents an integrable equation. So if I were going between 2 points, let's say our 2 points are defined by pressure 1, volume 1, temperature 1, and we're going to end up at pressure 2, volume 2, temperature 2, then I can integrate this equation so that it looks something like this. I'll integrate on the volume side from V1 to V2, R over V dV, and I can take the constant out of this. So let's do that just to simplify this. And we'll end up with a very familiar equation. All right, this is going to be equal on the other side, and again I'm going to take the constant out of the integration, but we're going to be integrating from T1 to T2 of dt over t. So this equation looks actually the same on both sides, except on one side it's involving volume and on the other side it's involving temperature. So if I were to actually evaluate this integral, I already know that this is going to give me log of V2 over V1. And this integral is similarly going to give me log of T2 over T1. So we're basically getting the same integral in both cases. But in this side, I'm multiplying by r, and in this side by negative CV. And now I can set them equal to one another. All right, now here's where I'm going to have to invoke a little bit of mathematics, and again, I apologize that it's going to look a little bit messy, but I want to take this particular expression here and use the ideal gas equation of state to simplify that. Actually, I'm not going to simplify it, it's going to look even worse, but let's see what it gives us. So when I go up here to the ideal gas equation of state, I'm going to take T2 over T1, and I'm going to use my relationship here for the ideal gas equation of state, and simply say that this would also equal r times T2 over r times T1, because I can multiply both numerator and denominator by the same number. I haven't changed the value here. Okay, but r times T2 is equal to P2 V2, and r times T1 is equal to P1 V1. Now here's the second item that I'm going to manipulate with this, and that is to say that if I have log of this ratio, log of T2 over T1, and I write this as log of P2 V2 over P1 V1, I can write this basically as log of the quantity P1 over P2 over P1, I'll get it right one of these times V2 over V1. And then I have a property of logs that says if I have the log of a product, that's equal to log of one plus log of the other. So I can rewrite this as log of P2 over P1 plus log of V2 over V1. So I've done all of this so that I can simply plug all of this in here for log of T2 over T1. So using this substitution, I'll be able to write negative CV times log of P2 over P1 plus log of V2 over V1. Now, we'll notice that I have a log of V2 over V1 here, and I've got a log of V2 over V1 here. So how can I bring those together so that I can do something even more interesting? Well, first I want to divide by this quantity here. So if I divide both sides by that, I'll end up with R over CV multiplied by log of V2 over V1. And that will be equal to negative log of P2 over P1 minus log of V2 over V1. So now if I bring this part over to this side of the equation, I'll end up with R over CV plus 1 times log of V2 over V1 is equal to negative log of P2 over P1. And once again, I'm going to use property of logs and say that anything that's a prefactor out here is like raising it to that power. And if I raise something to the negative power, I'm just taking the reciprocal of it. So I hope you can convince yourself that the properties of logs allow me to write this in this way. Now, this thing over here, this crazy combination of constants, I'm just going to define this as some generic constant, and I'll call it gamma. And we'll discuss in a moment what gamma is. All right, but whenever I have something as a prefactor in a log, I can use it to raise the argument of the log to that power. So I'll have, in the end, all of this, and let me separate this out a little bit. I'll have that log of V2 over V1 raised to this gamma power is equal to log of P1 over P2. All right, now whenever I have a log of something is equal to log of something else, that just means that this is equal to this. So I can now write V2 over V1 raised to the gamma power is equal to P1 over P2. And I hope that algebraically you can see that I can rearrange this equation a little bit so that it basically says that P1 times V1 raised to the gamma power is equal to P2 times V2 raised to the gamma power. All right, well, great. So I've got this nice, convenient, hopefully understandable result from all of this. But this is now telling me how curves on this PV diagram will vary when I'm on an adiabatic surface. That is an adiabat of this particular system. Now, when I have P1 V1 raised to the gamma is equal to P2 V2 raised to the gamma, that's really just a way of saying I've got PV raised to the gamma is equal to a constant. All right, now we've already seen curves where PV equals a constant. Remember, when PV is equal to a constant, this is what we have when we have an isotherm. So this is just a little bit different because we're raising V to some strange power. Now, when I look at this combination of constants, I can actually take this combination of constants and show that what do I have? I have R over CV plus 1. Well, that's R plus CV over CV. But remember, for an ideal gas, this is just the constant pressure heat capacity. So in fact, this gamma that I've defined is just the ratio of these two heat capacities. Since constant pressure heat capacity is greater than the constant volume heat capacity, gamma is always a number that's greater than 1, slightly greater than 1, but it's greater than 1, which means that the curves that I'm going to get that are represented by this particular set of equations, they're going to look a little bit like the isotherms, but they're going to be steeper than the isotherms. So we're going to come down like this. Okay, so these would be what I will call adiabats that represent curves where there is no heat exchange with the environment. And if I were to draw on this same curve what isotherms look like, remember those are also curves that come down, but they're not as steep. So they're going to look more like something like this. Now the main point in drawing these both on here is to emphasize the fact that when I'm on an adiabat, and I'm going, say, down this adiabat, I'm crossing several isotherms as I go. So in other words, temperature is not constant on an adiabat. So this thing that I wrote up here, not the same as isothermal, absolutely true. Adiabats do change temperature. They also can change volume, so they can show work, but what they cannot show is they cannot show any heat change with the environment. So this gives us a little bit of a clue into how to think about adiabats. We can think of them as curves that are very similar to isotherms on a PV diagram. They're a little bit steeper than isotherms, but we're going to see some examples of adiabats directly where it's going to matter that they're not on an isotherm. In fact, we're going to be creating cyclic paths out of pairs of adiabats and pairs of isotherms. I'm sure you're excited to hear that. But anyway, that's something that's going to come in the near future.